Today we are going to start with a new topic, that is the solubility product and the common ion effect, right? So first we'll be taking up the solubility product. So before we start, you should know that what is salt. I know that you know it very well now because we have almost completed the whole chapter of ionic equilibrium, so you're well versed with the salt. But still, if you have forgot that definition, so I'm just repeating it again for you, right? The salt is formed when acid react with base. When acid react with base, they result in the formation of salt and water, right? When this, you can say the salt is neutral when it is formed from strong acid and strong base, but if it is formed from weak acid and weak base, then it is neutral, or if there is slight difference between the chemical nature of the acid and base, means one of them is slightly acidic or one of them is slightly more basic, right? Then it is not going to neutral, it will possess the slightly acidic or the slightly basic character, right? So it can also be formed from the acid and base, like the strong acid and weak base. And if it is formed from strong acid and weak base, that means its nature is going to be somehow acidic, right? Similarly, if we have, instead of strong acid, we have the weak acid but the strong base, then obviously the nature of the salt is somehow going to be alkaline in nature, right? So that means salt can, the nature of the salt actually depends that from which strength of acid and base is used in forming that salt, right? So but now for this moment we are not concerned with these things. We know that we are already familiar, we know that when and where to use these things, right? You know the buffer solutions, you know the the salt hydrolysis, everything, you are well versed with it, right? But as far as the solubility is concerned, we are just concerned that what happens when salt is dissolved in water, right? As you all know, that's what do you mean by the solubility? What do you mean by the solubility? You know that concentration and solubility is different things, right? Do you know that? Concentration and solubility are two different things, right? Suppose I have the given solvent, and I add solute to it, right? So how much solute I add into the solvent gives my concentration. But when I talk of solubility, that means out of that whole solute which I added into the solution, how much moles of it are actually dissolved in the given amount of solvent. That means when we are talking about solubility, we concern the you can say that how many moles of the solute gets dissolved, right? And in terms of concentration, we just see that how many moles or is added to it, whether it is dissolved or undissolved. We are not concerned with it. But when we are talking about solubility, that means how many moles are actually dissolved in the given solvent, right? So you are familiar with the term solubility now. Now we are coming, I'm just coming to the point, what is the solubility product and what this topic refers to, right? I think it is very much clear in your mind that we'll be taking up the solubility of the salt in it, under this topic, right? So as we have seen that when we add salt to water, some salts are almost soluble, right? That means we add salt and it just gets completely dissolved, like NaCl, you know that, right? But some salts are moderately soluble. That means they are soluble but not up to fully extent. They get soluble but not 100% they get soluble, right? And we also get sparingly soluble salt. What do you mean by this term sparingly soluble? That means their solubility is very, very, very less, right? That means when we dissolve them in water, they don't get dissolved so much or 100%. They're, you can say they get dissolved only up to a small extent, right? So let me just state an example for you. Like it is PbSO4, it is BaSO4, and it can be PbCl2. It can be AgCl. So there are many salts, like that means the salts of the first group maximum, they are sparingly soluble. That means they get dissolved in water but up to a very small extent, right? So that means the solubility is not same for all the salts. Some salts are very soluble, some salts are moderately soluble, and some salts are sparingly soluble, right? So what happens when we add the sparingly soluble salt, that means the salt of these categories, into the water? What actually happens? When we add, it is in solid form, right? When we add into the solution, it becomes aqueous. Then it gets ionized. but we know that it doesn't get fully ionized. We know that because it gets dissolved up to a very small extent. Suppose I am explaining you, suppose I add AgCl to water, what will happen? Not all the AgCl molecules will go into the water, right? First point. Or not all the AgCl molecules are going to be going to get into the water, right? Out of them, only few gets dissolved. Only few actually goes into the water, right? And what happens when and out of those actually few which went into the water, they only get fully dissociated, and the ones which do not get into the water, they remain undissociated, right? So that means in this the dissolution is also occurring and the precipitation is also taking place. So I can write that, see, we have taken AgCl solid salt, we add into water, it becomes AgCl aqueous, right? That means dissolution is taking place. And this amount of AgCl which goes into the water, it gets completely ionized to form Ag and Cl, right? But it doesn't get ionized to a fully extent. There exists a dynamic equilibrium. That means they are getting dissociated, and these dissociated ones have the ability to combine and again precipitate, right? So that means precipitation is also taking place simultaneously, right? So that means there exists an ionic equilibrium in this. There exists an ionic equilibrium in this. That means the you can say the rate at which the AgCl get dissociated into AgCl is equal to the rate at which Ag and Cl combines to form AgCl, right? So that means there exists a dynamic ionic equilibrium, right? So let us write the equilibrium constant expression for this. So it comes out to be K is equal to concentration of product. So we have these two products. So I am just writing the concentration. You know it very well that we enclose them in bracket, and the bracket means concentration, right? And there is a product sign, not the +1, divided by concentration of the salt, right? This I have taken. So this is you can say is a solid form, and these are in the ionic form. And if we can write this expression as this also. So I have just multiplied it with this. We can write this way. You also try in your copies. It is not a big task, right? As we know, as I've told you while we were studying the characteristics of the equilibrium constant, we told you that for the pure solid and for the pure liquid, we take the concentration as 1, right? So that means in this AgCl concentration is not changing, right? So that means it is constant. So we can take it as 1. So AgCl multiplied with the equilibrium constant give rise to Ksp is equal to Ag positive, Cl negative multiplied, right? So what is this Ksp? Ksp indicates the solubility product. So we can say that if somebody asks you to derive an expression for solubility product, so first thing should strike in your mind that solubility product is written only for the salts which are sparingly soluble, right? Then you should know how to write this, that dissolution is also occurring, taking place, as well as the precipitation is occurring place. You know how to write this, show this equilibrium, ionic dynamic equilibrium. You should know how to write a chemical equilibrium, equilibrium constant expression, and then by just shuffling them, we have K into AgCl solid, which comes out to be Ksp, that is the solubility product. So if somebody asks you to define solubility product, how you are going to do that? So it's so simple. You just have to say that the solubility product of the salt is equal to the concentration of the product of the concentration of the ions in which it gets dissociated, right? So this is the solubility product. Like now one more important thing you have to remember in this case, as in AgCl there was 1 mole of AgCl and 1 mole of Ag formed and 1 mole of Cl negative formed, right? But what happens if there are 1 mole of this and this is 2 or this is 1, means they are not, the product and reactant are not equal in their number of moles. What happened in that condition? How this equation gets modified? So see, I am just giving an example. So let it be Ca3PO4 whole twice. What's that? You know that, calcium phosphate, right? It is calcium phosphate. So how it is going to dissociate? Obviously you know how to split in ions, right? But what you get to see in it, that it has 3 atoms, right? 3 atoms will be converting into ions. So that means you need to multiply it with the 3. That means the superscript will be the stoichiometric coefficients or the moles which are used. The similar we did in equilibrium constant expression. Same in this case. So it comes out to be this, right? So suppose we take in concentration of this as x, so that means it is x cube, and if we take the concentration as again y, so it comes out to be 2. So it matters a lot, right? So we have to consider the atoms as well as moles involved, right? Like, because in this it was 1 mole and they were forming the 1 mole expression. That is why we just wrote that Ksp is equal to the concentration of Ag positive and Cl negative, because the mole was 1. But if it is not 1, then we have to do it in this way, right? I think it is clear. So this is a solubility product, right? Now one thing I would like to discuss with you, that we have done the ionic product of water. Do you remember that? That yes, water is a weak electrolyte, it dissociates to form H positive, OH negative, you know that. So Kw is equal to H positive concentration. I'll write for you. We did an ionic product of water. So by ionic product we know this, right? And by solubility product we have an expression. Suppose I take an ion A positive, I am taking a general expression, right? So what is the difference between this ionic product? This I am considering for water, we can take in general the ionic product, right? So what is the difference between the ionic product and the solubility product? They are two different things, right? What is the first difference? First difference is that in case of solubility product, it is applicable only to the saturated solutions, right? That means Ksp, the solubility product is valid only for the saturated solutions. That means which cannot dissolve as much as solute we add into it, right? So it is applicable only for the saturated ones. But when we talk of the ionic product, it is applicable to all kind of solution, whether it is saturated, unsaturated, supersaturated, or anyhow. It is valid to all kind of solutions, right? So this is the first point. Again I am repeating, it is valid only for the saturated solutions, and it is valid for the any kind of solution we take into account. Don't get confused with this Kw. It was just to show you that it was like you did the ionic product of water, we can take out the ionic product for any compound, right? Any weak electrolyte. Now the second point is that when we talk of Ksp, its value is actually constant at constant temperature. Suppose if we take a standard, if we see at standard temperature, then its value is going to be definitely constant. It actually varies along with the temperature, right? But in case of the ionic product, when we take into account, its value actually just depend upon the concentration of the substances. That means it doesn't change with the change in the temperature, it changes with the change in the concentration of the substance, right? So this is the solubility product. I think you got it completely. So if somebody asks you about the solubility product, you need to say that it just determines the solubility of salt in water. That's it, right? Then if somebody asks you for a mathematical expression, just take an example or a general one, just write in this way and show it that it is equal to the concentration product of the concentration of the ions formed by the weak electrolyte, right? And if somebody asks you that if there are change in the number of moles in reactant and product, then you say that this equation just get transformed into this one. They are just raised to their, those moles just become the stoichiometric coefficient. They are written as superscript, right? But they matter a lot. Like if you are given a concentration of Ca, suppose as x or 2, right? So 2 cube means something, right? If you will take only 2, it will be different value, and if you will take 2 cube, it will be something else. So that means these values are very important. You need to remember that, right? And when we talk of the solubility product and the ionic product, you should know the difference that exists between them. It is applicable to the saturated solutions, and ionic product is applicable to all kind of solution. It is irrespective of the nature of the solution, right? And second is that the solubility product value is just depend upon the temperature. At constant temperature, it is going to be constant, but for ionic product, its value just depend upon the concentration. As the concentration will change, and obviously the ionic product is going to change. So this is how we explain the solubility product. Now we will be taking a few numericals, right, based on this solubility product.